Hello everyone. First, let me welcome you all in this online 2-week refresher course in natural sciences, organized by the Teaching and Learning Center, Ramanujan College, in collaboration with the Department of Chemistry, Rajdhani College, University of Delhi, under the aegis of Ministry of Education, Pandit Madan Mohan Malviya, National Mission on Teachers and Teaching. I would like to thank all the members of the organizing board, but especially one of the program directors, Dr. Poonam Pepil. Thank you, Dr. Poonam, for being so uncomplaining. Hello, everyone, once again, and I am Shakib Ahmed, an associate professor at Physics Section, Women's College, Aligarh Muslim University, Aligarh. Since this is a refresher course on natural sciences, so it is very obvious that I'm going to have a mixed faculties or audience, out of which not all are well versed in physics subject. So that's why I have decided to choose a topic of very general interest. The topic is the mystic universe. I hope I will be able to justify the topic because this is such a vast area of cosmology and each and every word of it needs a full lecture series. However, I have tried to be very brief and discuss the interesting part within the time limit provided. So, physics has its reflection at the foundation of everything we can think of. Only physics can find the answers to the mysteries of the mystic universe, which are looking like impossibilities that may take 1,000 years or more to solve them. But I will start by asking few questions like what is universe? How large is the universe? What is the shape of the universe? What is the age of the universe? Does the universe has an edge or a center? Depending upon the shape of the universe, where and how does it begin? So we'll talk about the Big Bang also. So what is the fate of the universe? And how does it expand if it has no edge? What is the dark matter and dark energy? And there are many more questions which has to be answered. So these are some of the biggest questions, and while our existence is so small as compared to the existence of the universe, that we may never be able to fully understand the true scale of the universe. However, advancement in technology are helping us to look ever deeper into the mysteries of our existence towards the edge of our observable universe. In these 3 lectures, I'll be briefly putting in front of you the answers to few of these questions, like what is the universe, its ever-spreading scale, its beginning, its shape, and its phase, and the laws through which our universe governs. Basically, so let us start by asking what is the universe. So the universe is all of space and time and their all the contents. So how you define a space? A space is basically is the volume of the universe, the volume within the universe. And time it is the constant flow of course through within the space, which is working as a catalyst of life, death, creation, and evolution. But the space and time are fundamentally linked and they are combined to form a complex system, which we all know is space-time. So basically the universe includes everything that exists from the smallest particles we know, quarks and atoms, to the largest one, planets, stars, galaxies. All these together with all other forms of matters and energy are there in the universe. So the universe include visible, which we will call it observable universe, to which we can see, and beside that we also have invisible things in the universe, which we call as a dark universe. So the first natural question comes into mind, that how big is the universe? So to feel that how big is the universe, uh, let us come to this our Earth and Moon system. And we live somewhere in this beautiful and very big planet, which we call Earth, which is around 12,700 kilometers in diameter. And everything which we all come across throughout our life is itself in this planet Earth. Have you ever thought that this such a big planet Earth, how big it is as compared to the universe? So let us first compare it with our nearest satellite Moon. It seems to be very close to the Earth because this is one to which we always see very clearly in the night or sometimes in the day too. But actually the Moon is not so close to us as we think of it. It is quite a distance away from us, the Earth. It is almost 400,000 kilometers from the Earth. So much that we can fit almost 30 Earths in between the Earth and the Moon. Now let us see how our beautiful Earth looks like from the surface of the Mars. This is one picture. Uh, this is one picture which has been taken from the Mars through the space probe. So this little dot which you are seeing is actually our Earth, which is like this from the surface of the Mars. So the average distance of the Mars from us is 400 million kilometers away, or could be more than this. Even light will take almost 20 minutes to reach us from the Mars. Then if we compare our Earth with the Sun, our Sun, we know this is Sun-Earth system. So you can see that our Earth Moon system is there as compared to the Sun. The Sun is like 1.39 million kilometers in diameter, and which is basically 109 times greater than that of the Earth. So over 1 million Earth we can fit inside this volume of the Sun. The Earth is about 1 astronomical unit. That is the 1 astronomical unit is the average distance between the Earth and the Sun is called an astronomical unit. So that is equal to 150 million kilometers. So the Earth is about 1 astronomical unit away from the Sun. So the astronomical unit is the distance between the Earth and the Sun. So you see that the largeness of the universe just as compared to our Earth and the Sun, if you compare our Earth and the Sun system. This is our solar system in which we live. So there are 8 planets, several dwarf planets, thousands of asteroids, and trillions of comets and meteorites which are roaming around the Sun as the center. So we have Sun, we have Earth, and inside that we are expanding. I'm zooming out to see that how vast the structure of the universe is. So once we get out of our solar system, if I get out of from our solar system, what we see is the interstellar neighborhood. This is our outer solar system. You see that this is our solar system. So here we measure the distance when we get out of the solar system. We measure the distance in terms of the light year instead of the astronomical unit. So the light year is a unit of astronomical distance, which is equivalent to the distance that the light travel in 1 year. So we know that the speed of light is in vacuum is 3 into 10 to the power 8 meter per second. So with this speed, the distance covered by the light in 1 year is the one equal to the 1 light year, and this is equal to 9.4607 in 10 to the power 12 kilometer. That is basically 10 trillion kilometers. So the nearest star, so this is our solar system. The nearest star beside the Sun, which is you can see is Alpha Centauri, which is like from here to here, this 4.24 light years away from us. This region is within about you can see that is 40 light years away. So our solar system is within the 40 light years away. So that means if light start to travel from this corner to this corner, it will take 40 light years, okay, to travel from this corner to this corner. So if we zoom out more, then we can see our Milky Way galaxy, where our Earth is located at one of these. This is Milky Way galaxy. This is the center of the galaxy. These are the moving spiral arms. So our solar system is located at one of the arm of this Milky Way galaxy. So you can see this Milky Way galaxy in this image of the night sky above the Paranal, which is in Chile on 21st July 2007. This is the Milky Way. This is this is the edge of the Milky Way galaxy to which we belong. So at the center of the image, you have two bright objects are visible, this one and this one. So you can see that the brightest is the planet Jupiter, and the other is star Antares. So suppose that you are sitting on one of the spiral arms of in the solar system, and you are seeing the other part of your Milky Way galaxy. So here you can see a video of how if we observe the night for many days, then we can see that this is how our galaxy Milky Way looks alike, from sitting at the center of the Earth, being centered as an Earth. So so beautiful and vast as compared to the tiny part of this galaxy in which we live. But our galaxy uh, is a spiral galaxy, in the center of which a supermassive black hole is supposed to be there, named as Sagittarius A. And the Milky Way is a spiral galaxy, is a giant disk of stars, and it is you can see that our solar system is located here, which is about 33,000 light years away from the center of the galaxy. Our whole galaxy is more than you can see 10,000 light years across from this corner to this corner. If you measure from like diagonally, then this is like 10,000, 100,000 light year across. Okay, so in this galaxy there are almost 100 to 400 billion stars and planets, but we cannot see all these in the night, because all the 99% stars which we can see at because this is our solar system, all the 99% of star which we can see is just located in this smallest area, where our Earth is located. So the Milky Way is approximately 899 billion times the mass of the Sun. So this such a vast galaxy is nothing as compared to the system of which Milky Way is just a tiny part. So nearby our Milky Way, you can see nearby our Milky Way, there exists another galaxy named as Andromeda galaxy, which is M31, which is actually 2.5 million light years away. And the other galaxy is here, which is known as the Triangulum M33, existing nearby. In the future, the Milky Way and Andromeda galaxies are expected to collide in about 4.5 billion years, and then they can form another astronomical system. So you can see this video of collision of this Andromeda galaxy and the Milky Way galaxy, and they keep on colliding until they form a different astronomical system. You can see this simulation. But if we zoom out this, we can see which is known as the local group of galaxies. Uh, there you can see this is our Milky Way. Uh, this is our Milky Way. This is Andromeda galaxy, and this is Triangulum galaxy. So if you are zooming out from this Milky Way to the further in the universe, so we see which is known as the local group of galaxies. This is the part of our space, which is the collection of 54 other different galaxies, which are distributed within 6.5 million light years. Okay, so if you further zoom, then we can see the Virgo supercluster. You can see here is the Virgo supercluster. So the local group of cluster is a very small part of the Virgo supercluster. So here these are distributed within 130 million light years, and but in this it's a huge cluster, which is a thousand of galaxies are there, and the largest cluster is the Virgo cluster. But such a big supercluster is also a very tiny part of a supercluster, which is known as Laniakea supercluster. So Laniakea supercluster is a home of almost 1 lakh galaxies of our Milky Way galaxies. So this is almost 500 millions light year in dimension. So if we could further zoom out from here to the observable universe, then we can see uh, that this uh, Titanic Laniakea supercluster is also just a small part of the universe to which we see today. This is how the universe, the simulation of the how the universe looks like, is like kind of resembles to a web called the cosmic web. So this structure is based on the survey of the galaxies, which reveals a web-like or honeycomb structure to the universe, which contains great walls, kind of walls are there, filaments are there, and it also contains voids, which where we have no galaxies. So probably at least 100 billion galaxies are there in the universe. So as we move further, but the universe we talk about is known as observable universe. This contains everything to which we can see and observed. This contains at least billions of galaxies, and we cannot count the number of stars which are inside these galaxies are there. It could be more than the dust particles in the desert of our Earth. So if you suppose if we centered if we suppose this is the center as an Earth, so the distance to any corner to the observable universe uh, is uh, is is observed to be 46 billion light years. This is 4650 crore light years. So the whole radius of this whole diameter of this observable universe out of this space, and this is just 46 billion light years is just the observable present universe, which is like 92 billion light years in the diameter. But the important point to be keep in mind that the presently reachable universe by us is only this red area, which is 14.5 billion light years across. So that means what we have seen in the universe is only within this diameter. This is presently observable, but by reachable by us is this only 14.5 billion light years. But the most interesting thing is that what is outside this observable universe, which is what is beyond this yellow region. Mind it that the observable universe is all those objects to which we cannot see. Observable universe is to which we can see or observe today using the advanced technology and telescopes. It is most possible that the universe beyond this observable universe is many more times bigger and interesting. We cannot even think about those possibilities that we will be going to encounter beyond this observable universe. Why? Because we cannot see it from this point in space and time. We cannot see from this beyond this yellow region, because the light has never been reached to us from that far, or may not reach to us, never. So the reason is that our universe is expanding with the speed more than the velocity of light. We will talk about this later, the expansion of the universe. So it is very clear that if we live here more than billion of years, even then we cannot see or observe all those many places of this infinite universe. no matter how hard we try to observe them, because the cosmic information theory, which we also take up later, this what is cosmic information theory, that suggests that the whole universe could be around 10 sextillion, that is 10 to the power 23 light years across. Or the present calculation model says that it could be 250 times bigger than the observable universe, which is 92 million light year in diameter. So 250 times this area is bigger, could be the whole universe. So now you can think of that, how big our universe could be. Just for the sake of imagination, you can think of that we are living inside a football, and compare to this with the whole universe as an earth. So you can imagine the football and the earth size. So this is where this is our earth where we are living out. This is the whole universe. So but you see that the universe is full of many more mysteries to be undiscovered, and scientists are constantly doing their interests with latest technology which are available. So moving further, if I ask how big the universe is, seems like a silly question. I mean, it's big, really big. But how big is the universe? Well, the first thing we need to realize that there is a difference in the entire universe and the universe visible from the Earth. So because these are two different things, entire universe and the universe visible universe. So how much of the universe we can see from our Earth as a center? We know that the light has a speed of 3 into 10 to the power 8 meter per second. It means that when we are seeing an astronomical object, uh, then we are seeing it as it is in the past. So the time taken by the light is coming, because uh, we know that, for instance, when we see this astronomical object, we see it as it was in the past, because the time has lapsed while this light uh, emits from here and then reaches to us. Because we know that in case of if we have a sun earth system, we know that uh, the light from the sun to get to the earth almost 8 minutes. This we all know from the high school. So uh, the sphere idea is true in general. So if there is a sphere around the earth with a radius of 2 light years, and we blink some light at the edge of the sphere, suppose that some lights are coming from these galaxies, then we will travel towards the earth, and they will reach to the earth after 2 light years from the same directions. So that means that when we saw these lights, so I'm seeing these galaxies as they were 2 light years older, located at the edge of the sphere. So we can take this idea to the extreme and can ask that what is the oldest thing in the universe, and that is by definition is the moment uh, when the universe begins, and that happened 13.8 billion light years ago. So this will be 13.8 billion light year ago. So if the universe was not expanding, then the fastest or oldest thing we would see would be a sphere centered around the earth with the diameter of 13.8 light years. So mind it, because we are supposing that the universe is not expanding. So this is what we call observable universe. So universe, all that exists is observable universe is all that exists, and observable universe is all that we can see. And this is observable universe, and we cannot see outside this sphere. So within this visible universe, light takes time to reach to us. Outside the universe, it has not. So we cannot see anything outside this sphere. But we have to be cautious, because the number quoted for visible universe is feasible when the universe is not expanding. So remember that the universe could be infinite, and the observable universe is most definitely finite. So but we know that the universe is expanding, so we will discuss it later. So the situation is little more complicated. So if the universe is expanding, so the bottom line is that there is a sphere centered at the Earth up to the extent of the visible universe. So, is that how big the entire universe is? That centered 13.8 billion light years? The answer is almost certainly no. The universe is way bigger than what we currently see now, and we already knew this. So if you look out the light from the edge of the sphere coming to us today, so if you look at if we are sitting here today, if the lights which are coming from the edge of this sphere, uh, but if we look it out tomorrow, then we will have to add some more visible space to it. That have to add some more visible space to it. That because the light travels during those 24 hours is getting here tomorrow. So day after day we will be able to see a larger and larger sphere of the universe. First day, second day, and third day. There are locations that we cannot see today. It is simply because the light from that is simply not have reached to us today, but we will be able to see it tomorrow. So this idea solves the complication due to the expansion of the universe. Therefore, we can conclude that the entire universe is definitely much larger than the portion we see today, which is known as the observable or reachable universe. But the question remains to answer how big it is actually. We need a number. So we will take this up on the later stage. Well, to answer that question, we need to back up a little bit. Uh, Let us now talk about the expanding universe. In these slides, I will try to or make you understand that how we come to the conclusion that really the universe is expanding within the presence of the dark matter. Not only expanding, the universe is actually accelerating under dominance of the dark energy. The first thing we ask, is the universe expanding? And how do we know that the universe is expanding? So the answer is given by the scientist Edwin Hubble in 1920s. He introduced the concept of cosmological redshift, and to prove that beside our Milky Way galaxies there are other galaxies existing, like the one earlier looked like a nebula, which are actually different galaxies. The most important discovery is the expanding universe, in which he observed that the galaxies were moving away from each other and had given a law known to us as the Hubble's law. The statement of the law is that the farther away a galaxy is, the faster it is moving away from us. So this is a Palomar 48-inch telescope which Hubble used for this sky survey, and this is the Hubble telescope named after Edwin Hubble, and is roaming in our universe, sending very important information to these days. So next few slides I will show you the observational evidence for the expanding universe model. So here you see this is hydrogen lamp spectrum, hydrogen gas lamp. When we excite the hydrogen lamp, and we get the hydrogen emission spectra. So this is hydrogen emission spectra. Concentrate on this red line, and note that the hydrogen emits the light at a specific wavelength. So you can see hydrogen, and similarly other elements too emits their respective spectra, like helium. So this is for the helium spectra, we can see. So if you look at the light in the same way, if we look at the light from the sun, because sun is a hot ball, so we must observe the following spectrum, and using the spectra of the absorption lines from the sun, we can infer which elements are present in its layers. So hydrogen, sodium, iron, calcium, magnesium, oxygen, etc. We can infer the presence of these elements using these absorption lines. As we can see that we can excite this hydrogen gas inside the lamp, we get this emission spectra, and we see that this is the particular uh, fingerprint of the hydrogen gas. So in the same way, this lady, which is Cecilia Payne, discovered what the universe is made of. She also discovered what the sun is made of. She is the reason we know anything about the star, a star whose brightness as seen from the earth fluctuates. So in this context, uh, we have see this Orion nebula. Nebula is actually the region of space which is enormous clouds full of gas and dust particles. So this nebula is a star forming region in our own galaxies. So it is made of mostly hydrogen. So if we take the fingerprint of this spectrum, so we can see the fingerprint of the hydrogen line, especially the strong, if you concentrate on the strong red line, which is at 656 nanometer is present. The nebula also has a lot of oxygen, which is accounts for the extra green lines in the spectrum. So you have to concentrate on this hydrogen line, which is here. So if you're moving further uh, uh, to different galaxies, here is the spectrum of the fairly distant galaxies, which is UGC 12915, a picture in the upper left. It has a lot of hydrogen that glows as an emission line in the spectrum too, but a lot of hydrogen lines here. But pay close attention to the location of this 656 hydrogen line. In the next few slides, we will see that galaxies at further and further distance. So if I say that the distance of these galaxies are getting further and further. So for distance, which is evidenced by their decreasing apparent size. So in their digital sky survey image. So if you see this galaxy, this is getting further apart. You can see the spectrum here. Also, this you can see the position is like red line, hydrogen spectrum. Similarly, so we can see that similarly this is another galaxy getting further apart. See this hydrogen line, and then this is more further apart, and you can see this is another galaxy. So almost the hydrogen line is redshifted, no, is to some another region. So the hydrogen line 656, which was here earlier in those galaxies, is redshifted all the way into the infrared region. So I have basically collected all these spectra at one place to see a better picture. The only conclusion you can infer from here is that uh, as we look further away, the line shifts towards the red end of the spectrum. So if as the galaxies are moving further and further, this red line is moving to red region. This is red region moving further and further away from the red region, and this completely goes to the infrared region. But why these lines have moved? We all know the similar kind of phenomena. We call it Doppler effect. That when a train is coming towards us, the frequency of the sound wave increases, and while going away, the frequency decreases. But this is not Doppler effect. It is a kind of redshift. And this is known as a cosmological redshift. And this is due to the velocity of the galaxies which are receding away from us. So the galaxies in the universe are receding from us. So because of those velocity, this shifting of this line are there, which is known as the cosmological redshift. So this is a mathematical formula through which we can calculate the velocity, receding velocity of the different galaxies. This is the lambda observed wavelength of the line observed in the stars, and true wavelength is the line which we can have in the lab here itself on the earth. and then c is the speed of light. So we can, if you know these things, then we can calculate the velocity of this particular galaxy which is receding. You can see this picture, a spectrum of galaxy which is NGC 1357. Look for the two specific lines which are calcium K and calcium H lines. We can calculate the velocity of this galaxy with the help of these two lines of absorption spectrum. So actually the limited true value is the value, limited true value is the value, this uh, which is the wavelength in the lab on Earth for the same element, for the calcium. And for example, we have, if we take calcium alpha, so we can put we can calculate the wavelength of this from this spectrum from the star, and which is lambda observed, and the true value from the lab, we know c is 3 × 10⁵ kilometer per second. So we can put it here and we can calculate what is the receding velocity. Similarly, from this line we can calculate, and then if we take the average of these two velocity, we get pretty accurate value of the recessional velocity of this galaxy as observed through the sky survey. So this is because of the redshift we have. This is a plot of recessional velocity. This is on the y-axis we have recessional velocity, and on the x-axis we have distance for several galaxies. These dots are for different galaxies. So this data, if you fit this data is fitted with this equation v equal to h naught d. So this h naught is the Hubble constant, and which is in the unit of kilometer per second per megaparsec. Basically, the parsec is like 3.26 light years. That is 13.9 to 10 power 12 kilometers. So h naught, because this is a straight line, h naught is basically the gradient of this straight line, or the slope of this straight line. This will be del v times del t. So if we can calculate the value of h naught from this graph. So if we take this value, this is 2000. If recessional velocity is 2000 kilometer per second, then the corresponding distance is like 9 × 10⁻20 kilometers. And then if this is 4400 kilometer, then the recessional velocity is like 20. So if we put all these things, then we can find what is the value of the gradient. This is h naught. So this is 67.73 kilometer per second megaparsec. So this is quite close to the observed, which is like h naught, which is 71 kilometer per second per megaparsec. So the important conclusion we can make that the greater the distance of the galaxies is from us, the faster it is moving, or faster it is not moving, it seems to be receding. Another important point to be noted is that look at the unit of h naught. So h naught is per second. Okay, so this is the Hubble constant. So it is a second inverse. It means that if we run the expansion backward, we can estimate the age of the universe, just like we can have t equal to 1 by h naught. Okay, so we can calculate the age of the universe. So t equal to 1 by h naught, we have value of h naught, which is 2.2 × 10⁻18 seconds. This is this much of second. And then if we convert this second into a year, so we have, you know how to convert it, hours to 60 into 60, 60 minutes into 60 seconds. This is 3600 seconds. Day we have 24 hours, and in year we have 365 days. So if you calculate it, it comes out to be like 14.5 billion years, which is quite close to the present accepted number for the age of the universe, that is 13.8 billion years. So as I already told you that the redshift is not the Doppler effect. This cosmological redshift happens due to the expansion of the space-time itself. because when the space-time stretches in itself, the wavelength stretches and shifts towards the red region of the electromagnetic spectrum. So please don't get confused with the Doppler effect and between the Doppler effect and the cosmological redshift. These are like its analogy is same, but they are the different things.